Yeah, hi everyone. Welcome to Multimodal Weekly. For those of you who are new, this is a weekly webinar series hosted by Qualitative, which is where I'm working at. We are in early stage startup focusing on building multimodal foundation models for video understanding. This is an initiative that we've been doing over the past year or so to really basically gathering a community of folks who are interested in the intersection of multimodal AI and video related projects. Some of the topics that we tend to cover on a weekly basis are obviously research, right? Because I think it's definitely a very new field that requires a lot of innovation. So we have researchers coming and talk about multimodal foundation models, etc. But occasionally in the past, we have industry practitioner. So that can include like entrepreneurs, startup founders, developers, talking about their respective projects, application in different verticals. And we have like team members in the past sharing guides and tutorials on how to use a platform and API. Over the past several weeks, I've been really doubling down on the research community because I think, there's a lot of excitement in, things like vision language model, general like a seminar multimodal, in a lot of conferences, in this year so far. So these are the kind of speakers that we brought in, like folks working in, video summarization, alignment in, evaluation of multimodal LLMs, video segmentation, data problem, etc. So for today's session, we have two really exciting presentations that I cover really like different aspects of working with different tasks related to like multimodal and video. The first speaker is going to be Andrew Rouditchenko, currently a PhD student at MIT CSAIL, and he's going to talk about his project called Whisper-Flamingo, which basically combine and fuse the audio and visual element within video to enable tackling speech recognition and translation tasks. And the second speaker is going to be Soumya Jahagirdar. I'm correctly spell your last name. I think now you're a PhD student in the University of Tubingen in Germany, but I think you're going to talk about your master thesis work, right? That you did back in your grad school in India that focused on video question answering on videos with textual element inside. And then finally, we'll conclude the webinar with two speakers from KAIST in South Korea. So Geon Yeong and Hyeonho. They will give a talk on video motion customization using a diffusion model. So basically focusing on the generative models for with video. So I think it's also like super exciting because we need to talk about both the discriminative tasks as well as generative tasks. So I'm excited to hear the perspective on how things going on the generative side of things to understand video and work with video better. So with that, just a quick logistical note. Feel free to send your question on Zoom chat for the attendees, and then I will surface them with the speakers after they finish. So with that, I will stop sharing my screen. And Andrew, I will unmute you. And you can go ahead and share your screen and start your presentation.
Okay, great. Thank you very much for the introduction. Hello, everyone. Super excited to be here and present about Whisper-Flamingo. And in this project, it integrates visual features into Whisper for audiovisual speech recognition and translation. And this work was conducted with the following co-authors, and it was published at InterSpeech 2024. So in recent years, there's been major advances in speech recognition models. And these types of models can cover two different types of tasks now. They can do speech transcription, meaning that given audio, the model outputs text in the same language, or even translating speech. So given audio, outputting text in a different language that was spoken in the audio. And one such model is OpenAI's Whisper model. And it's a very popular model because it was trained on around 100 different languages for the transcription and translation task. And it was released open source. So it's a great model to do off-the-shelf transcription of different audio. However, Whisper and most speech recognition models in general have a problem. that their performance actually decreases in noise. So this is a plot which kind of illustrates this problem, and this is a plot from the original Whisper paper. Basically, each line represents the performance of a single model, and we can see that as the noise level increases, meaning the SNR gets lower, so this is towards the right of the plot, we can see that performance actually gets worse. And we usually measure performance for transcription with word error rate. So higher word error rate means that the model is performing much worse. So this isn't really desirable. We'd like to have good transcription performance in all sorts of acoustic environments. So getting models that perform better in noise is always a question of interest. So there's one way to handle this is through audio-visual speech recognition. So basically, these types of models combine the information from lips to enhance the transcription performance in noisy environments. And the main idea is that if you're looking at someone speaking, then it's easier to like figure out what they're saying in noisy environments by tracking the movement of the lips, because that contains like information relevant to decoding the speech. And historically, these types of audio-visual models can be 2 to 3 times better than the audio-only models in a moderate noisy condition, for example, noise level of 0 SNR. However, there's a problem with training audio-visual models from scratch, and that problem is that there's not enough video data compared to just audio speech data. For example, Whisper was trained on around 700,000 hours of audio training data. However, a state-of-the-art like audio-visual model, AV Hubert, was only trained on 1.7 thousand hours of video training data. And as we all know, performance scales with data. So this is a problem that we wanted to tackle in this work. So the question that we asked is like, how could we improve the audio-visual models if we have that limited amount of video training data? And the way we wanted to do this was to basically take the Whisper model, which was already pre-trained on a lot of audio data, and somehow combine it with a strong visual speech encoder, for example, AV Hubert. And we wanted to basically convert the audio model into an audio-visual model. And as part of this project, we also wanted to investigate Whisper's strong multilingual capabilities. So it can perform English speech recognition, but it also does like recognition, translation of different languages. So in particular, in this project, we adapted it for English to X speech translation, meaning we go from English audio to multilingual text. So now I'll briefly describe the method of our work. So the first stage of our work is to make Whisper more noise robust. So Whisper is an audio-only model, and it's an encoder-decoder transformer. And in this stage, we fine-tune the audio-only Whisper model, and we add noise to the audio. So the noise includes different kinds of sounds. For example, side speech, it could be music, could be babble, where there's many different speakers talking at the same time. And in this stage, we fine-tune all the parameters of the model. And essentially, this just makes the model more robust to having noise in the input speech. The second part is where we add the visual component. And this is where we inject the visual features into Whisper. So what we do is we freeze the audio-only Whisper model, and we add these new trainable cross-attention layers into Whisper's decoder. And the cross-attention layers are attending to visual features from a pre-trained AV Hubert model. So basically, it's extracting representations of lips that are useful for like audio-visual speech recognition. And then during this stage, we're training the model on audio-visual inputs to adapt it to the new modality. And for more information on the gated cross-attention, this was inspired by the Flamingo model from DeepMind, hence the name Whisper-Flamingo. And in that work, they basically took a text language model and they injected the visual information into it using gated cross-attention. And this turns out to be like a very effective pipeline for introducing a new modality. And it's commonly used in like updated vision language models to get that vision capabilities. So inspired by this, we wanted to use the gated cross-attention to inject the visual features from AV Hubert into Whisper's decoder. And Whisper's decoder is sort of like a text-based language model decoder. So the pipeline is very similar to the original Flamingo paper. And for more details, the gated cross-attention equation is just shown below. It looks very similar to the standard cross-attention layers. And it's actually initialized as an identity function by initializing these alpha weights to 0 because tan h of 0 equals 0. So essentially what happens is that in the beginning, the model actually ignores the visual features because the gated cross attention is canceled out. And this equation just becomes x prime equals x and y equals x prime. And then over time, the model adjusts the weights of these alpha parameters, and it starts to learn to pay attention to the visual features through the gated cross attention. Okay, so besides the gated cross attention, we also add a new capability to Whisper, which is to perform English to X speech translation. And to remind you, this task is going from English audio to different text in different languages, hence the X in the task, English to X translation. And we did that by training on English audio and video paired with the English text to perform the transcription task, but also the translations in 6 different languages. So in the end, the model supports these different languages for the translation output. And this is a schematic of the architecture. So first off, you could recognize the Whisper architecture as the encoder-decoder model. And then we introduced the A.V. Hubert video model. And these are the new gated cross-attention layers, which are inserted into the decoder of the Whisper model. And as you can see in stage 2, all of the parameters of the different models are frozen except for the new gated cross-attention layers. So in a sense, it's kind of like a giant adapter being added to the Whisper decoder to be able to adapt to the new modality. And finally, we introduced like new English to X translation tokens so that the model knows to translate the English audio video to different languages. For the experiments, we used Mavic dataset, which is based off of LRS3. And that's a very common benchmark dataset used for audiovisual speech recognition. It has 433 hours of English video for training, 1 hour for validation, and 1 hour for testing. For the models, we use the 3 largest size of Whisper. And when we add the Whisper-Flamingo, when we add the gated cross-attention A.V. Hubert, that could increase the parameter size quite significantly. And finally, for the metrics, we use word error rate for English transcription, where lower is better, and blue score for English text translation, where higher is better. For the test scenarios, we test the model in the clean audio conditions, where this is the original audio in the test data set. And for noisy conditions, we add noise to the audio in the test data set. And what we did is we used Babel noise for these experiments, where we basically took audio from 30 different speakers and we added it together. And then we mix it with the audio that we're testing at a signal to noise ratio SNR of 0. And note that the noise is only added to the audio and not the video. And later on, I'll show you a demo of the testing. So first off, for the English transcription experiments, just to remind you, it's word error rate, so lower is better. We first have the Whisper audio model without fine tuning. So this is just taking OpenAI's model and applying it to our data set. So in the clean condition, we get a pretty good word error rate of 2.1 versus in the noisy condition, the performance gets much worse and it goes to 20.8. Then we have the result of stage 1 where we just fine tune the audio model by itself. And here we get a large boost in the performance in noisy conditions. So it's about twice as good. However, the clean performance gets just slightly worse from the original model. So it shows that fine tuning on noisy audio can help a lot for noisy case, but you might get a slight reduction in the clean condition. Then we have the result of our Whisper-Flamingo model, which uses both the audio and the visual components to do the recognition. And the performance in the noisy condition is much better, about twice as good. And also we get a slight boost in performance in the clean scenario. Finally, comparing to A.V. Hubert, which we use as like our visual encoder, we get similar performance in the clean condition and slightly better in the noisy condition. So next up, we have the performance for the English to X translation task. So in this task, we give the model the English audio and video, and we ask it to translate to all those 6 different languages. And then we average the blue score over those six languages. So again, we start off with the audio model. And this one we fine-tuned because it didn't support this task previously. So again, we see a decrease in performance in the noisy condition. Now we have blue score where higher is better. So the performance drops in the noisy case. And then we have our audio-visual Whisper-Flamingo model where we get a reasonable improvement in the noisy condition for the blue score. And then compared to the previous state of the art, we're doing better in the clean condition and just slightly worse in the noisy condition. However, the previous state of the art, the bilingual AV Huber model, they fine-tune separately per language, and they use a separate model for each target language. So essentially for the 6 different languages, they require a different model for each language. However, what we did was we trained on all languages, and we use a single model to perform all the different tasks like English transcription and the translation to 6 languages. So we think this is a more scalable approach for training on more languages, say 100 if we collect the data for it. And it's nice that our single model can perform all those different tasks. So now I'd like to show you a demo of the recognition performance. So try to predict what this person is saying. Yeah, did the audio come through for that?
Yeah, I think a little bit.
Great. So then here's our model's prediction. And this is the original audio without the background noise.
It's using past experience based on similar situations to try to make meaning.
So in the noisy condition, our model like effectively uses the lips, and it only got 1 word wrong in the noisy condition. And then this is a demo of like the translation capabilities of our model.
It's using past experience based on similar situations to try to make meaning.
Okay, and I have one more video to show which compares the original Whisper model as well. So this is the output of the original Whisper model when we just take it off the shelf and apply it to the noisy audio. And as you can see, it doesn't really do well with this type of noise. And then here's our Whisper version, which is fine-tuned. So when we fine-tune our model on noise, it does better at picking out some of the words, but really the major benefit is from fine-tuning using the lip information in Whisper-Flamingo. Okay, so in conclusion, our Whisper-Flamingo combines the strengths of Whisper, which is the audio-based speech recognition model, and AV Huber, which we leveraged as a video model using gated cross-attention in the style of Flamingo proposed by DeepMind. And our audio-visual Whisper-Flamingo significantly outperforms the audio-only Whisper model when tested on noisy audio. And our model performs different tasks, including English speech transcription and English to X speech translation. And finally, our method is general and could work with better audio and video models in the future. So for example, if there's a better version of Whisper coming out or a better lip reading model, then the gated cross-attention framework is quite flexible, and we could integrate both of those into our framework. And as part of this project, we were able to release the code, models, and demo on GitHub. And I've also prepared some like Google Colabs where you can play around with the model and like reproduce the videos that I made. So feel free to try it out and let me know if you have any questions. And these were the key references that I mentioned in this work. So thank you very much. Happy to take questions.
Great, yeah. Thank you, Andrew. Really awesome demos and comprehensive walkthrough of how it works and demonstrative, obviously powerful capabilities of your solution. So there was one question on the chat from Michael. He asked, "Good Whisper-Flamingo work with a live camera on a person speaking in a noisy environment?"
So thank you for the question. I don't see the chat. How could I access that?
So you're sharing the screen, right? So you can hover through your. Did you see any Zoom element?
I think I lost the Zoom Zoom controls. Let's see. Okay, I lost his. Oh, I found it actually. It was on my third monitor. So okay, thank you. So the question is, would it work with a live camera or a person speaking in a noisy environment? Yes, I think it could work The main constraint is that the video should have the person's lips visible. So if you have a video of someone speaking into a camera and their lips are mostly visible, then it should work. The main thing with our model is that it requires like some pre-processing, to get the video on the lips. So that's like an additional pre-processing step. But as long as the lips are visible, then it should work.
Awesome. Yeah, any other question from the audience? You can either put in the chat or you can just raise your hand and I can unmute you. Pranay, you got a question in the chat. You want to answer it?
So I see the question. Have you tried sparse gated attention or sparse attention to reduce the number of parameter increase? Yeah, so that's a good question. As I mentioned, that the gated cross attention actually can add a lot of parameters. So for example, I think for the largest Whisper model, it's already 1.5 billion parameters. And when I add the gated cross attention, it adds 600 million parameters. And it would be nice to try to reduce the number of parameters. So one thing they propose in the original DeepMind paper is to actually like do subsampling. So instead of adding the new gated cross attention in every layer of the decoder, you could try adding it like every second or every fourth layer. And that would probably like, that would decrease the number of parameters already by 4. So that could be something good. I personally didn't try that because my goal was to get like the maximum performance improvement, and I was willing to have a larger model. But that is something worth investigating. And also in terms of practicality, I did train smaller versions of the model, so using Whisper Small and Whisper Medium. And I did those so that there's a slight decrease in performance, but I do see a large improvement for the audiovisual model. And those models are released on my GitHub. So if anyone wants to try to use those for like more real-time application, like someone mentioned like a live camera feed, then that model would definitely work faster. So
great. Yeah, maybe another question. Are you in the Boston area?
Yeah, Boston. I am in the Boston area.
Great. I was taking a look at your website. It looks like you've been focusing on this problem, audio, visual recognition for quite a long time, right? I think your previous publication in previous year was on like audio visual segmentation, audio visual learning from video. How do you see like the evolution of this space over the past couple of years? From when you guys first started until now.
Mm-hmm. Oh yeah, definitely. Great question. So I've been working in the multimodal focused on audiovisual for a while. And I would say the field has kind of shifted over from self-supervised learning. So learning like good representations from unlabeled data through contrastive learning or, mass data modeling from both the audio and visual modality to more of like LLM and generation capabilities. So I think, what you guys are doing at 12 Labs is very exciting, and because it's kind of tackling this modern problem. So yeah, I would say it's always exciting, always something new. So happy to chat more research if anyone is interested offline.
Yeah, awesome. And then maybe another question is this will focus on speech translation as well, right? So you utilize the NX translation model for the 6 languages, right? You're thinking about like maybe expanding to like more multilingual setting, more power, like maybe by adopting a more powerful base like speech translation model. Yeah.
Mm-hmm. Yeah, definitely. So my original goal with this project was to be able to make it work on like videos in any language. With the current like Whisper-Flamingo 1.0 presented here, the multilingual capability was being able to translate from English to different languages. But one goal that I'd personally like to pursue, or the research community, is to make it work for videos in other languages as well. So for example, like the Mavic dataset actually has TED Talks in other languages. So for example, French, German, so that, that dataset has a lot of, interesting avenues to explore.
Awesome. Yeah, super excited to hear that, and yeah, look forward to more upcoming publication on this domain.
Thank you.
Yeah, thanks, Andrew. Yeah, so because we still have two other speakers, I will move forward to the subsequent presentation. So yeah, I will unmute Soumya, and yeah, do you want to go ahead and get started?
Yeah, just I hope the screen is visible.
Yep, I can see you.
Yeah. Hello, everyone. Thank you so much, James, for letting me give this talk. So today, I'm Soumya Jahagirdar, and this is a collaborative work with CVC Barcelona and IIIT Hyderabad. This was my master's thesis, but right now I'm a PhD student at University of Tubingen. So today I'll be talking about text-based video question answering, basically video question answering on videos that contain text. So as we all know, conversational AI has been here for a while, and I think it'll be there for coming more years. And we have a couple of interactions like human-robot, robot-robot, multiple home assistance devices like Alexa, Google Assistants. And all these capabilities have led to, led to tasks and data sets that would at the end help these kind of interactions. So mostly what people have looked into are visual question answering, video question answering, and extensions of these like captioning as well. So multiple data sets were introduced starting from 2014 to still today. There are new VQA data sets that have been introduced. Each of these look into different aspects, like let's say text VQA was looking into scene text present in the scene to get the answers for the questions. GQA mostly looked at elements and their objects and their relationships, whereas KVQA was mostly looking into the knowledge graph aspect of the visual image that was given into consideration, and then doc VQA, which mostly focused only on the OCR content present in the image. So a lot of these works look at different aspects of the scene, and similarly multiple other data sets such as text VQA, scene text VQA, doc VQA, infographic VQA, OCR VQA, and VisVis. All of these data sets mostly focused on the OCR aspect in the natural scene. So it was mostly to consider visually impaired people and how these applications would have a good social aspect to it. So a lot of these questions, like especially data sets like VisVis, was something which was focused more on visually impaired. So regardless, scene text does play a very important role, and that is what we were taking away from these data sets. So one way we looked into like the visual, just the single image aspect of it. But then there were works such as ActivityNet, Movies QA, TV QA, that mostly focused on question answering, but on videos where the questions would require multi-frame understanding. Like ActivityNet would require mostly where the questions were mostly based on the activity. Movies QA and TV QA were mostly based on the type of scene that was happening in the movie or in the TV series. To have a good recap, or let's say if we want to distinguish all of these work, we can simply consider them to be either text-based reasoning or temporal-based reasoning. So the first work was VQA, where there was no temporal or text reasoning needed. Scene text VQA, where text reasoning was needed, but no temporal reasoning. Whereas VideoQA was one where we needed temporal reasoning, but there was something missing. And that part was where we required both textual as well as temporal reasoning. So just to reiterate, we introduce a new task of text-based video question answering. So the way we set it up is as a multimodal task that aims to automatically generate answers to the questions about textual content given in a video. So what best videos are there for text than news videos, right? Because we have news videos everywhere we have them in different languages, plus we have them in different categories like sports, educational, or it could be even like health, sports. All sorts of videos are present in news videos. So we picked news videos as the main source of for this data set. So as we introduce a new task, we did not have any data set for now for this task. So we also propose a new data set called as NewsVideoQA, where what we do is we take up, I think, around 15 different news channels and their playlist, and we get videos from different types of videos like sports, educational, Omicron, and crypto news, which are like belong to different categories. So what we do is first we get these random set of videos, news videos. We clip them into 10 seconds, and then we ask annotators to make questions for these videos. So we have certain set of instructions where we ask annotators not to frame questions which are more generic in nature, such as what's the name of news channel, because these questions would be common for all the frames or all the videos. We don't want redundant questions. And questions that mostly were based on advertisements, because we wanted initially to stick with questions that belong to either of these categories that we had selected. So that was one of the restrictions that the annotators had to consider. Also, we did not have any limitations onto how many maximum number of questions each video clip should have. Each video clip has minimum of one question, but maximum extended up to, I think, 30 questions per video. Not 30, 12 questions per video. So yeah, we did not have any restrictions over how many maximum number of questions could be framed using a single video clip. So we had to create one annotation tool where people could, write in their question, add the answer, also the timestamp at which the question was framed. So just to reiterate or focus here is that the timestamp which was added by the users, annotators, was where the question was framed, not where the answer is. So this is something that we use in our experiments. So yeah, this is just like a brief, a good overview of how the dataset looks like. We take news videos from multiple news channels such as BBC, Fox News, CNN, CGTN, and so on. We end up having 3,000 odd video clips with 8,600 question answer pairs. And we also have another version of the same dataset, which we call NewsVideoQA V2, which has 10,000 questions and about 4,000 video clips. So we add more question answer pairs to the same dataset. So the basic annotation was done using annotators, and we had two annotation stages, where annotators would actually add questions, and the second stage was called verification stage, where the annotators or the verifiers were given the question as well as the video, and they were asked to type the answer. At the end, we retain only the questions that have same answers in both annotation and verification stage, so as to have a consistent set of questions and to have good quality of questions. So unlike all the other just like all the other data sets, we also have certain charts that talk about how the data set looks like and what's the average question length, average answer length, a number of OCR tokens per frame. And then we also give top 15 most occurring questions answers as well as OCR tokens. So just a quick glimpse of how the data set looks like. So as you can see, these questions are mostly related to crypto news, where we also have questions with Omicron, because this data set was taken when in 2021 end. So a lot of questions a lot of videos are actually from Omicron, Corona type of videos. So yeah, some more images. So as you can see, the type of, so there are different cases and different types of frames. So some frames, especially Indian news channels, have a lot of text coming in and going out, whereas the other channels have little text in them. So there is variability of number of tokens per frame within the data set. So in order to benchmark, we tested on 3 different baselines. One, which is a very natural extension, would be BERT, where instead of giving any context, we give OCR tokens as the context. How do we get the OCR tokens? Which frame do we pick? We have a good set of ablations which we do. So I'll be talking about that in the further slides. And the question is the question that we have. We also tested out on a baseline called as M4C, which is basically a model for text VQA and STVQA dataset, where the input to the model is not just the OCR tokens and the question, it also considers visual features from faster RCNN. So again, remember that this work was done in 2021 and there are better models now. So yeah. And we also tested on VideoQA method because as it is a video question answering dataset, it would make more sense to also test it on a VideoQA method. In this case, it is singularity. So a lot of these video question answering datasets require only one frame to answer the questions. So that is what this paper singularity proves. So we were like, okay, if this is where the current VideoQA benchmark stands, then why don't we take the best working model here and then try it out? So basically what this VideoQA model does is it trains using just single frame while pre-training the model. Pre-training tasks are caption generation. So given a random frame, but a single frame, the task is to generate a caption. And they fine tune it on video question answering and video retrieval tasks. And at the time of inference, what they do is they randomly pick a certain set of frames, concatenate the visual features, and then pass it along with the question to get the answer. So that is at the test time. But at the train time, it's just a single frame that they use. So we extend this VideoQA model to also consider OCR tokens because our data set mostly looked into the textual part in the video. So what we do is we continue the pre-training, which was done in Singularity by now doing caption OCR text generation rather than caption generation. And we also fine-tune it on our dataset on NewsVideoQA, where along with the text encoder, which was just the questions in the previous model, we also concatenate it with OCR tokens, so that it gets more incentive on to look at the OCR tokens. So just to have a heuristics on how the data set is. So what if I pick the answer that occurs in my data set maximum number of times and test it on the test set? So it turns out that 3% of the times I can answer it just by picking the most common answer. So we also check how, what if I pick the biggest OCR token in the frame or in set of frames, and how do we get the answer? So what if I pick the biggest OCR token and compare it with the actual answer? Turns out that biggest OCR token has doesn't have a lot of influence over the answer, what the answer is, because the answer could be a very small number as well in the image. And we look at vocab upper bound, substring single frame, substring all frames, where vocab upper bound accounts for the answers that are common in test and train set, and substring single frame basically checks if the answer is present in a single frame. And here the single frame is picked where the question was defined. So what if I take a single frame where the question was defined, get OCR tokens for that frame, and check if the answer is present in that frame or not? So that is how we do the substring single frame. And then for all frames, we just concatenate OCR tokens from all the frames and see if the answer is present in either of them. So just to again tell you all is that 74 or 76 is a number which we usually consider when the answer is present in the OCR tokens. So obtaining answer with textual information could also mean that it could be a binary question as well. It could be yes or no. So this score does not account for that. Yeah, so here, this table basically shows what if I just give one frame while training, and then what if I give just one frame while testing. So as you can see, BERT QA, which is a text-only model, when given a random frame, performs as good as a model that also takes visual information. So it could be weird for now, but then we will talk about that in further slides. Why is this happening? And here you can see that BERT-QA, when given OCR tokens from where the question was defined, performs really well without any visual information. So here are more results on different number of frames used for testing. So what if I give more than one frame? As you can see, BERT-QA performs very good when we give like 2 frames on which question was defined. And all the other models perform like not as good as BERT-QA. So which leads to certain questions and drawbacks about the data set as well as how current VideoQA / VQA, syntax VQA methods have been designed. So we'll talk more about that in the next slides, but these are some qualitative results. So just to conclude, we did introduce a new task and a data set, and we checked how this new data set performs on a couple of baselines that are already there. But we do have some limitations about that, or we can say we have some observations. So dataset, first thing is that this dataset contains only news videos. What we want is to have more different types of categories. And then also text-only model performs better than any multimodal or any multimodal method, be it VideoQA or VQA method. So what can we do next? So in the next work, what we do is we explored this another data set called M4 White VQA, which was released at the same time as NewsVideoQA was released. But this data set has 9 different categories rather than just one. So it's like shopping, traveling, video games, driving, and so on. There are 9 different categories. And yes, the questions are again framed on the text content present in the video. So just like a slide that shows statistics about this data set. More statistics, which I'll skip. Yeah, they also introduce a new method similar to OCR-aware singularity, but they also add a vision language transformer where instead of having just visual features, they also add video-based features that they add in this model. But there are some things that were common in both the data sets. So one thing is, what if I black out the entire image, but just keep the text part in the image? Can I still answer? Me being human, can I still answer this question? Turns out it's true that I can still answer just by looking at the text. Another thing, what if I just pick one frame? Well, how do I pick the frame is definitely a question. But let's say I know where the answer is. What if I just pick one single frame and try to find the answer? Is it possible for me to get the answer using just a single frame? Turns out, yes, in most of the cases. So in order to have like a good quantitative evaluation on how many of these questions do actually require multi-frame understanding in both the data sets, and how many of these questions require actual visual plus textual understanding to get the answers. So what we do is we do a small exploratory data analysis where we randomly sample 100 question answer pairs from both the data sets and check for certain attributes, such as if the question is answered by only single frame, how many questions require multi-frame understanding, similarly for how many questions require just visual information, how many questions require only textual information, and how many frames are actually crowded with text where the question was defined. And we also look into what type of answers are present in the dataset. Are most of the answers extractive, or answers reasoning based, or the answers knowledge based? So looking at the graph, it just it makes us realize that most of these questions in both the datasets require single frame understanding and just textual information to get the answers, which is very which negates the fact that these are video question answering datasets. So so in order to prove this more empirically, what we do is have a very exhaustive analysis on BERT-QA for both the datasets. So what we do is we train BERT-QA model on, we simply just test it on the T5 White VQA dataset. That is 9 different category dataset. And then we also fine tune BERT-QA, and we see that in most of the cases, the scores are higher compared to T5 VideoQA. So remember, accuracy is exact match when the generated answer is equal to the correct answer, whereas BERT-QA actually depends on the OCR tokens accuracy. So if the quality of the OCR tokens is not that good, then the accuracy what we expect is would decrease. But that is the only reason why the accuracy here for T5 VideoQA is more compared to the BERT-QA. Otherwise, as you can see, ANL is for all the splits, ANL score for BERT-QA is better than T5 VideoQA. And remember, this is not even a visual transform. It's just text VideoQA. It's just text QA model. And T5 VideoQA, on the other hand, is a huge video transformer model. We do the same thing with the NewsVideoQA dataset, where we check for what if I take 12 random frames, what if I take a single frame, what if I take single correct frame, and then what if I concatenate OCR tokens from 1 frame per second. So it turns out that when I get more context for the model performs better as expected. We also check for a couple of questions. So M4 VideoQA dataset has these categories called easy, hard, text, and vision. And as you can see, in all the cases, in all the 3 cases, those are easy, hard, and text. BERT-QA performs better. Vision, it does not perform as good as T5 VideoQA, but it's just there. The problem with these data sets is not the fact that they don't have visual questions. It's just that the number of questions that require visual information is way too less compared to the other type of questions. So that was mostly the takeaway that we were able to observe in both the data sets. So we did some cross-domain experiments when we train on BERT-QA on one data set and then test it on the other. And we see that it helps sometimes. So here are some results where just BERT-QA without fine-tuning and with fine-tuning, how does it help? This is for the M4 VideoQA dataset. More qualitative results on what happens if I do cross-data training. So, and again, the conclusion here is that this is basically a study that provides that current text-based VideoQA datasets majorly focus on extractive answers. The degree of visual understanding and multi-frame comprehension needed to answer these questions is very limited. And we just show the effectiveness of BERT-QA, that is just a text-only model, in achieving comparable performance to multimodal methods. It's also partly the multimodal methods, but it mostly is the data set that needs to be looked into before we even frame. But the problem is that while we define these data sets, it's very difficult to have this controlled question answer generation. And that's why recently, like multiple automatic question generation systems have been coming into picture. So I think that would help. But nevertheless, data is something that's that everyone needs to look into. So just what next? There could be some couple of future directions, which could be non-extractive answers. How do we actually frame truly multimodal questions? Can we have an automatic procedure for generating these QA pairs? And what if we look into question answering on educational videos, like biology, if we take example of biology, and what if we try to make questions on those which require both text as well as information about the diagram, which could be there in the scene or the slides. So yeah, couple of references, and yeah, data set as well as code for the works is there in my page and my GitHub. So feel free to reach out, and yeah,
Awesome.
I would be happy to take questions.
Thanks a lot, Soumya. Thanks for really being extensive and going over, different threads of your work. For the audience, if you have any question, feel free to put on the chat, and I think we can. I think you can answer them asynchronously, since we still have another presentation. Time a little bit crunch. So, so let's do the Q&A for your session via Zoom chat.
Yeah.
Awesome. All right. So Jeong Yeong and Hyeonho, I'll unmute you guys, and you can go ahead and talk about your work.
So is there any problem with my presentation? Or...
We are seeing your notes and your slide.
Okay, so is it
Okay.
fine?
Yep. Now it's working. Yep. It's working now.
Okay, great, thank you. So let me just point out my pointer. Okay, so great. So hi, my name is Geon Yeong Park, and it's a great honor to share our work in this webinar. And thank you, James, for hosting us. And today I'm going to talk about VMC, which is a video motion customization framework, which edit the input or generated video using the diffusion models. And as you know, the video generated models are becoming more and more important to model the visual intelligence. So it is the initial version of video generated model, which is released about 2 or 3 years ago. And in a short period of time, yeah, we can see a lot of progress in this quality and fidelity. And so, you know, there's a lot of other global contenders like Dream Machine from Luma, Beacon Labs, or Gen 2 AI, etc. So there's a lot of progress in this foundational video general models. And I would say like this video revolution is mainly empowered by the progression of diffusion model. And, you know, the diffusion model is kind of iterative refinement process, which gradually denoise an initial noise vector to the clean image. And while it is started as a image generative model, people are now extending this diffusion model to the video modeling. So, for example, people often have to start with a pre-trained image model and add a new temporal dimension to the model. And then they trying to fine-tune or train the model with a larger scale text-to-video dataset. So in order to model the temporal dynamics and relationship within the video, there should be some architectural contributions or innovations to make this come true. And one is the temporal convolution or temporal attention layers, which inherently learn the relationship or similarity between the video frames. So in common video diffusion models or other layers, spatial layers like self-attention or cross-attention layers, they are not for learning the interaction between frames. So all the temporal relationships are about learning the great temporal attention layers or convolution layers. Here's a figure about the temporal attention layers. And another pioneering advance in architecture design was the cascaded model design. So what I mean by cascaded is a step-by-step pipeline design. So here you may do not want to generate a high-dimensional final output at one shot. Rather than you may start with a generating low dimensional or low resolution keyframes. So like, for example, if you have input text like sprout in this shape of text imaging, you may want to generate a low dimensional or low quality keyframe, which is very short in temporal. And then after forwarding these keyframes with frame interpolation model or spatial super resolution model, then we can get a complete generated output with a high quality and high resolution. So after having this kind of foundational video diffusion model, our next step would be like how to control the generative process or customize the generated video in a way we want. And, you know, obviously we are talking about video, so you just may want to take control over the motion, like moving object from here to there, or so forth. And we call this problem as motion customization, and which is quite related to the appearance customization or personalization, if you know the context in diffusion model. So this motion customization might remind you this kind of dream boost like task. So in personalization or appearance customization, our goal is to keep appearance of the cute dog and in different context or background. And in motion customization, yes, we want to reproduce the exact motion, but in different visual appearance or context, like changing the background or subject. So you may think about this motion customization like a motion version of Dream Boost or personalization task. So we now define the problem of the motion customization. So for this motion customization, we have two important problems. First one is how to define the motion pattern. And second one is how to learn the motion with video diffusion prior. And both is quite important, where the first one is non-trivial to represent the motion dynamics. And the second one is more about the model parameter, learning parameter, model architecture design, etc. So since we have talked about architecture point so far, so we first move on to the second point, the model design part. So our first point was that we have to customize the video diffusion model in computationally efficient way. So as our goal is to generate a realistic video, we have to preserve the original generative capacity of the original diffusion model. So that's why we have to kind of limit the scope of fine-tuning parameters. So we don't want to change the diffusion model all over, but we want to preserve the original capacity and change a little bit of parameter for our input video so that we can customize the motion pattern. And also we obviously have to minimize the training time taken for the customization. So we don't want to take like 20 or 30 minutes for customizing one video. So we have to reduce the training cost. So from this perspective, what I have observed in here is that I have mentioned about the cascaded design. So here we have keyframe generator, and we found out that the keyframe generator is a key for motion control in the whole cascaded pipeline. So as in this figure, the keyframe, 3 keyframe already determine the overall temporal layout of the video. So after passing through the frame interpolation, we can see that this motion is quite improved, refined, but the overall temporal layout is consistent. So our goal is to, so this motivates us to focus on the keyframe generator during our customization, optimization. So we freeze the other components, the frame interpolation model or super resolution model, but we have to fine tune the keyframe generator with our input motion pattern so that we can customize to the our interested motion. So with this freezing, we can now enable the lightweight computationally efficient training with a single GPU chip under taking 5 minutes. And within this keyframe generator, another our focus is on fine-tuning the temporal attention layers, which encode a temporal prior. So it is responsible for modeling temporal dynamics and motion. So again, in keyframe generator, we do not want to fine-tune all over the layers, but we keep frozen the self-attention, cross-attention, or other spatial layers. And our focus is on the temporal attention layers. So we fine-tune the keyframe and we fine-tune the temporal attention layers. So this kind of architectural design contribute to the lightweight training. Okay, so we have talked about the architectural point. So let's move on to the learning parameter. So how to define the motion, how to represent the motion pattern and formulate the loss function. So here we first take a very simple but effective approximation for motion pattern, which we call as frame residue or motion vector. So this motion vector or frame residue means a difference between consecutive video frames. And as we can see in this figure, we can see that the background appearance or color information is quite removed out. And this allows us to disregard the visual appearance and just focus on the motion field. So which direction this pixel would move. So this one kind of remind you optical flow, if you know. So our objective is to learn this motion pattern or motion vector called delta V0 in here with our customizing diffusion model SOTA. So here we have delta V0 hat, which refers to our predicted motion vector. And we have delta V0, which is our original motion vector. So we want to align our input original motion pattern to our predicted one. So here's some detailed figure. So here the predicted motion vector delta V0 hat comes from the frame difference in denoised estimate or posterior mean of the video diffusion model. If you are not familiar with diffusion model, you can just think about it as a intermediate representation or prediction of the diffusion model. So this is quite blurry at the first state. So we have denoised estimate V0 hat in here and take the frame-wise difference as our motion vector prediction. So our observation is that aligning this original motion vector and our predicted one is equivalent to matching the epsilon residual delta thanks to the 2D formula or the relationship between posterior mean and the epsilon square. So I don't want to deep dive into this equivalence derivation, but from the implementation level, it is quite straightforward and easy. So if you are interested in this derivation, please refer to our main paper. So from the implementation level, here we diffusion forward the input video frames. And so we have a ground truth noise here, epsilon, and we have a noise latent in here. So we have consecutive residue as delta epsilon. And after denoising with a keyframe generator, we have a predicted epsilon zeta. And our observation is that aligning this original delta epsilon and our predicted delta epsilon zeta leads to the motion distillation by learning the motion vector field of the input video. So this one would be our motion distillation objective. So here's a final overview of our VMC framework. In customization training stage, we fine-tune the temporal tension layers of the keyframe generator using the motion distillation objective, which comes from the input motion vector. And in the inference stage, we take a DDI inversion process which preserves the overall structural consistency and denoise this inverted noise using the fine-tuned keyframe generator while keeping frozen the temporal interpolation and super resolution models. So here we use a new prompt, which is in a different visual context and appearance, like we want to change the seagull to chicken or changing the background, as you can see in the result. So yeah, here's some summary or overview of our result. I just want to skim through the overview. So if you're interested in, please refer to our project page or main paper. So you can see that we can change the background or the foreground object with the text prompt. And we can also change simultaneously both the foreground and background objects right here. There's some other output examples like this. So we can change quite complicated appearance context, like changing rabbit to squirrel and adding the sand or beach. Here's another examples. And one other thing is that like this one, the motion pattern would be quite complicated. Like for example, this one included the turning around motion with some overlap. And this one is quite a typical example other video diffusion models suffers from, but in VMC, we can see a lot of improvement. And comparison to baseline, like Video Composer Gen 1 or others, ours reflect the underwater new context more better. Here's another track examples. So for the quantitative comparison, we have done both automatic evaluation and human evaluation in terms of text alignment and temporal consistency, and we can see that ours outperforms others. And also there's a lot of some interesting applications like video style transfer, so that we can conduct style transfer, which remind you like image style transfer, like oil painting style. And another interesting findings was like we can enable learning backward motion, like a reversed version of a real world video. So this one is quite interesting because the original video diffusion model may not have some good prior about this reverse motion, but with our VNC framework, we can generate some realistic backward video. Here's another example. So yeah, so that's all. And brief summary, I can say that the two primary contribution of our VMC was fine-tuning the temporal attention layers for computational efficiency customization. And the other one was motion distillation objective, which represent or approximation of the motion representation. And for the future work or future direction, I think more and more video works are considering about how to approximate the motion representation in efficient and effective way. And one of our next study was like spectral motion alignment, which aligns the motion vectors in spectral domain, so we can represent the motion in frequency components, because the video motion would be quite well represented with frequency, like the bird or something like that. So if you are interested, please refer to our project page or our original main paper. So yeah, that's all. So thank you for attention, and I would happily take any questions.
All right. Thanks a lot, Jeong, for the complete walkthrough. Yeah, I also put the link, both VMC and the spectral motion alignment work on the chat as well for folks to follow. Is there any like direct question right away for the speakers? We're running like 10 minutes over time, so this won't be my full time for folks. If there's not like any immediate question, I think you can email Hyeonho, email here, like for context. Okay. Looks like there's no immediate question right away. Yes, thanks for putting the email, Geon Yeong. Yeah, like super exciting work. I think video generation spaces keep evolving, and yeah, excited to see more advanced method that can handle both like temporal understanding, but also like generate high qualities keyframes with compute efficiency. I think like the combination of both performance and compute trade-off, right? I think those are going to be some of the team that will need to address. But the future it sounds like strong upcoming works will handle that motion understanding, motion alignment specifically well. So we are excited to see that being published at different conferences. Yeah, so thanks for all the speaker again for making the time today to present your work. Andrew, Soumya, and Jeong, and covering different aspects of multimodal, right? From recognition to question answering to the diffusion models with generative capabilities. And yeah, I think there's a lot of exciting work that's going on in the field right now. And if you found this session informative, yeah, we run the webinar on a weekly basis, so you can tune it in for subsequent weeks to like hear more researchers talking about their exciting work. The recording of this session will be available on YouTube probably within a month or so, and I'll be sure to email the link to the speaker so they can share that with their social media and network. Thanks a lot for making time again today, and yeah, thanks to the attendees for attending, and yeah, I hope you all have a good rest of your weekend. Bye-bye. Thank you.